Picture this: a gathering of stars so ancient they witnessed the dawn of the universe, drifting through the cosmos, not as we expect, but moving in reverse, almost as if they're traveling backward through time. This isn't the opening scene of a science fiction film. It's real. Astronomers have observed a globular cluster, an enormous family of stars called NGC 3201, that appears to orbit in the opposite direction to the spin of our own Milky Way galaxy. It defies expectations, upends our models, and invites us to reconsider what we thought we knew about motion, gravity, and time itself. What does it mean for something to orbit backwards through time? It sounds like poetry, or maybe magic, but it's grounded in precise observation and painstaking science. This cluster's motion challenges fundamental principles of physics, hinting that there may be forces or histories at play which we have yet to fully understand. Perhaps it's the invisible tug of dark matter, the aftermath of a galactic collision billions of years ago, or even something more profound, something that touches on the nature of time and space. Whatever the cause, this celestial anomaly doesn't just belong to astronomers, it belongs to all of us, to anyone who's ever looked up at the night sky and felt that tug of wonder. In this video, we're going to venture together into the heart of this mystery. We'll explore how scientists made this mind-bending discovery, what theories might explain it, and why it matters not just for our understanding of the cosmos, but for our place within it. From the subtle whispers of relativity to the bold possibilities of quantum gravity, we'll traverse ideas that stretch the imagination. So settle in and open your mind. You're about to embark on a journey that will change how you see the universe, time, and perhaps even reality itself. It all started with a careful, almost routine observation. Astronomers were studying the motions of stars within a particular globular cluster known as NGC 3201, a dense sphere of ancient stars orbiting our galaxy. They were using incredibly precise data from the European Space Agency's Gaia spacecraft, a mission dedicated to charting a three-dimensional map of our Milky Way by measuring the positions and velocities of over 1 billion stars. As they analyzed the cluster's path through space, something immediately stood out as strange. The entire cluster was moving in a direction that was fundamentally at odds with the rotation of the galaxy itself. While the vast majority of the Milky Way's components spin in a particular direction, like water swirling around a drain, this cluster was going the wrong way. This wasn't a subtle difference or a minor measurement error. The data was clear and consistent, confirmed by cross-referencing with observations from powerful ground-based telescopes. The stars within NGC 3201 were on a retrograde orbit, meaning their trajectory was opposite to the galactic spin. This discovery sent a genuine ripple of excitement and confusion through the astrophysical community. It was as if they had watched a river for centuries, understanding its current, only to suddenly find a massive whirlpool spinning upstream. This anomaly challenged a very basic expectation in orbital mechanics, that objects born from the same rotating cloud of gas and dust should generally continue moving in that same direction. The finding forced scientists to confront a fundamental puzzle. This wasn't just an academic curiosity. It was a direct contradiction to established models of how globular clusters behave and how they interact with their host galaxy. The backward motion suggested that this cluster had a history far more complex and violent than anyone had previously assumed. It hinted that NGC 3201 might not be a native of the Milky Way at all, but rather a cosmic immigrant captured from another system that had long since been absorbed by our own. Or perhaps it had undergone a dramatic gravitational encounter, a close call with another massive object that violently redirected its course billions of years ago. The discovery opened up a profound line of inquiry, pushing researchers to look beyond standard explanations and consider a much wider, more dynamic cosmic history. To truly appreciate the strangeness of NGC 3201's backward journey, we need to step back and understand what globular clusters are in the first place. Think of them as the ancient elders of our galaxy, dense, spherical cities of stars, each containing hundreds of thousands or even millions of members, all bound together by their mutual gravity. They are among the oldest known structures in the universe, with many, including NGC 3201, forming over 10 billion years ago. That means these clusters were already ancient when our own sun and planets were just a swirling cloud of gas and dust. They are cosmic time capsules, preserving the chemical composition and dynamical history of the early universe, offering us a direct window into a time when the first galaxies were just beginning to assemble themselves. For centuries, astronomers have been fascinated by these shimmering orbs. In the 1700s, Charles Messier catalogued several of the brightest ones, mistaking them for comets through his small telescope. It wasn't until the 20th century that we truly began to understand their nature and their place in the cosmos. We learned that these clusters don't reside within the main disk of the Milky Way. Instead, they populate a spherical halo that envelops our entire galaxy, tracing out its vast gravitational field like moths circling a flame. For the most part, their orbits are orderly and predictable, governed by the steady, dominant pull of the galaxy's center. They are the dutiful satellites, following the rules of gravitational motion as set down by Newton and refined by Einstein. This long history of observation established a firm expectation. Globular clusters are ancient, stable, and predictable. They are the bedrock of galactic archaeology, their motions telling a consistent story of a galaxy's growth and evolution. That's why the discovery concerning NGC 3201 was so jarring. Located approximately 16,000 light-years away, this particular cluster is not an outlier in age or composition. It fits the profile of a typical globular cluster. But its motion is anything but typical. It acts like a rebel, a nonconformist moving against the galactic grain. This defiance forces us to re-examine the entire life story of such clusters. Perhaps their histories are not always so serene. Maybe the halo of our galaxy is a far more dynamic and violent environment than we ever imagined. A place where gravitational encounters can rewrite an object's destiny billions of years after its birth. The extraordinary path of this one cluster suggests that the textbook picture of these ancient systems might be missing a few crucial and incredibly dramatic chapters. So this idea of moving against the flow, of orbiting in the opposite direction, is what astronomers call retrograde motion. It's a concept that might sound strange at first, but we actually have examples of it much closer to home, right here in our own solar system. Think about a planet like Venus. From our perspective on Earth, Venus appears to rotate on its axis in the opposite direction to most other planets. It's a slow, backward spin, and while it's not an orbit, it gives us a familiar example of retrograde movement. Even more common are the moons that exhibit this behavior. Several moons orbiting the gas giants Jupiter, Saturn, and Neptune travel around their planets in a direction opposite to the planet's own spin. These celestial objects are like cosmic rebels, going against the established rotational grain of their parent bodies. The key to understanding this lies in a fundamental principle of physics: the conservation of angular momentum. When a star system or a galaxy forms from a collapsing cloud of gas and dust, that cloud has a certain amount of spin, As it collapses inward, that spin accelerates, much like a figure skater pulling their arms in to spin faster. This process sets a default direction of rotation for everything that forms from that cloud: the central star, the planets, and their moons. For an object to then orbit in the opposite direction, something significant must have happened to it after its formation. It didn't just start out that way. Its path was dramatically altered by a powerful external event. This is why the retrograde moons in our solar system are so fascinating. Their backward orbits are thought to be the result of dramatic gravitational encounters, perhaps being captured by their planet's gravity after forming elsewhere, rather than being born in place. Now scale that idea up to a staggering degree. We're no longer talking about a single moon being captured by a planet. We're talking about a globular cluster, a massive ball of millions of ancient stars moving in retrograde around an entire galaxy. The sheer energy required to flip the trajectory of such an immense structure is almost beyond comprehension. It points to a history of incredible violence and upheaval. This isn't a gentle nudge, it's a gravitational shock of epic proportions. Scientists theorize that such a dramatic reversal could be the result of a close encounter with another massive object, like a dwarf galaxy or a particularly dense clump of dark matter that effectively acted as a gravitational slingshot. Alternatively, it could be a lasting signature of the cluster's origin, suggesting it wasn't born in the Milky Way at all, but was captured from another galaxy that was itself moving in the opposite direction when it was consumed by our own. This single observation of backward motion forces us to consider the most dynamic and chaotic chapters of our galaxy's history, events powerful enough to redirect the course of a million stars. So if an event powerful enough to redirect an entire star cluster seems almost unimaginable, what kind of force could actually accomplish such a feat? One of the most compelling explanations points to the relentless, subtle, yet overwhelming power of gravity acting over billions of years. This isn't the simple, straightforward pull between two objects that we learn about in school. This is gravity on a galactic scale, a complex and chaotic dance involving countless players, many of which we cannot even see. The leading theory suggests that the retrograde orbit of NGC 3201 could be the result of gravitational perturbations, persistent tugs, and nudges from other massive bodies that have gradually but profoundly altered its path through the cosmos. Imagine the cluster's journey not as a smooth, predetermined arc, but as a meandering path through a crowded and ever-changing gravitational landscape. Over its immense lifetime, it has likely sailed past other globular clusters, through the diffuse halos of dark matter that surround galaxies, and near smaller dwarf galaxies that are themselves orbiting the Milky Way. Each of these close encounters, however distant they might seem, exerts a tiny gravitational pull on the cluster. Individually, these tugs are Chinese letter, insignificant. But when you compound them over millions and billions of years, their effect accumulates like water slowly eroding a canyon wall. This cumulative effect can gently break the cluster's original motion, or even provide just enough of a sideways kick to eventually flip its entire orbital direction. The specific mechanism at play here is a fascinating process known as dynamical friction. It's a concept that might sound contradictory. How can friction exist in the near vacuum of space? It's not friction in the traditional sense of two surfaces rubbing together. Instead, think of it as the gravitational drag an object experiences as it moves through a cloud of other particles. As a massive cluster like NGC 3201 plows through the sparse field of stars and dark matter in the galactic halo, its immense gravity pulls these surrounding objects slightly toward it, creating a wake behind it, much like the wake trailing behind a speedboat. This wake, dense with matter, then exerts its own gravitational pull back on the cluster, acting like a brake and slowly sapping its energy and momentum. This process is exceptionally efficient at altering the orbits of very massive objects, and over cosmic timescales, it can dramatically reshape their trajectories, potentially even leading to a complete reversal of direction. Sophisticated computer simulations have been crucial in testing this very idea. Astrophysicists can create digital twins of our galaxy, populating it with millions of virtual stars, clusters, and dark matter particles, and then set the simulation in motion to watch billions of years of evolution play out in a matter of days. These N-body simulations show that close encounters with other massive structures can indeed provide the necessary gravitational kick to put a cluster on a retrograde path. Perhaps NGC 3201 had a near miss with a particularly dense clump of dark matter, an invisible structure whose gravity alone gave the cluster a powerful slingshot effect. Or maybe it was a historical interaction with a dwarf galaxy like the Sagittarius dwarf spheroidal, which is currently in the process of being torn apart and absorbed by the Milky Way, its own stars being scattered into our galaxy's halo. The challenge, and the reason this remains a theory rather than a confirmed solution, lies in the incredible precision required. To prove that a specific past encounter was responsible, scientists would need to know the exact positions, masses, and velocities of all the players involved billions of years ago, a near impossible task. The evidence is circumstantial, written in the present-day motion of the stars. This gravitational sleuthing is like trying to reconstruct a single car's entire cross-country road trip based only on its final parking spot and a faint skid mark, with no map or GPS history. The clues are there, but putting together a definitive case requires piecing together a story from fragments of evidence, leaving room for other equally compelling explanations to emerge. But if gravitational nudges from visible objects offer one compelling explanation, there's an even more mysterious and pervasive force that could be guiding this celestial dance: dark matter. We know that the matter we can see, the stars, the planets, the glowing gas clouds, accounts for only a tiny fraction of what's actually out there. The overwhelming majority of the universe's mass is invisible, a substance we call dark matter because it doesn't emit, absorb, or reflect any light. It's completely transparent, yet its gravitational pull is the primary architect of the cosmos, sculpting the very large-scale structure of the universe. It's the hidden framework upon which galaxies are built and the invisible glue that holds them together. Now, imagine our Milky Way galaxy isn't just surrounded by a smooth, spherical halo of this dark stuff. Instead, picture it as a lumpy, uneven cloud with dense clumps and vast, empty voids. This isn't just speculation, it's a key prediction of our best models for dark matter. As the universe evolved, dark matter is thought to have collapsed under its own gravity, forming these intricate structures. Some of these clumps could be incredibly massive, containing the gravitational equivalent of thousands of galaxies, yet remaining completely invisible to our telescopes. It's within this invisible, lumpy landscape that NGC 3201 is traveling. The theory is strikingly elegant. As the cluster moves through its long orbit around the galaxy, its path isn't just a simple ellipse dictated by the smooth, combined gravity of all the stars at the center. It's also constantly being subtly tugged and warped by these localized, powerful concentrations of dark matter it passes along the way. If the cluster happened to spend a significant part of its journey moving through a region dominated by one of these massive dark matter clumps, the gravitational influence could be profound. This invisible hand could have gradually steered the cluster, applying a persistent pull that over billions of years altered its momentum, eventually flipping its direction entirely. It's a bit like a sailboat being pushed off course by a powerful, unseen current flowing beneath the surface of the water. This idea doesn't just solve one puzzle. It connects the strange motion of a single star cluster to one of the greatest unsolved mysteries in all of physics. If this theory holds, then NGC 3201 isn't just an astronomical oddity. It's a potential detector. Its unusual path could be our first real clue to mapping the invisible, lumpy distribution of dark matter in our own galactic backyard. By carefully tracing its orbit backwards and running sophisticated simulations, astronomers might be able to infer the location and mass of the dark matter structure that supposedly perturbed it. This transforms the cluster from a subject of study into a powerful tool, a cosmic probe allowing us to sense something we can never directly see. The backward orbit becomes a fingerprint left by the invisible hand of dark matter, waiting for us to decode its secrets. While the invisible hand of dark matter offers a compelling narrative, there's another grand cosmic drama that could fully account for this backward motion, a story of galactic piracy on an unimaginable scale. Our Milky Way is not the serene, isolated island universe it might appear to be. It is a cannibal. Throughout its long history, our galaxy has grown not just by forming its own stars, but by actively consuming smaller, neighboring dwarf galaxies, tearing them apart with its immense gravity and absorbing their stars into its own halo. This process of galactic mergers and acquisitions is a fundamental part of how large galaxies are built, and it provides a perfectly elegant explanation for the rebellious path of NGC 3201. Imagine a small dwarf galaxy, itself a collection of billions of stars, orbiting the young Milky Way billions of years ago. But this satellite galaxy wasn't moving in a polite, orderly fashion. Perhaps its entire orbit was retrograde, meaning it was circling our galaxy in the opposite direction to the Milky Way spin. Nestled within this dwarf galaxy was a beautiful, dense globular cluster, what we now call NGC 3201. It was born there, and it moved with the rhythm of its parent, sharing its retrograde trajectory. Then, over eons, the inevitable happened. The relentless gravitational pull of the much larger Milky Way began to strip stars away from the dwarf galaxy, stretching it into long, streaming arcs of light in a process astronomers call tidal disruption. The smaller galaxy was being devoured. During this violent assimilation, most of the dwarf galaxy's stars were scattered, lost to the vast halo of the Milky Way. But globular clusters are exceptionally robust and tightly bound by gravity. While the dwarf galaxy itself was torn apart, its globular cluster, like a precious jewel knocked loose from a setting, survived largely intact. It was captured by the Milky Way's gravity, but it retained the original motion it had from its parent galaxy, that distinctive backward velocity. It's a cosmic case of inherited property. The cluster kept the family heirloom of its retrograde orbit even after its original home was destroyed. This would make NGC 3201 not a native-born citizen of the Milky Way, but a naturalized immigrant, its unusual motion a lasting testament to its extragalactic origin. This isn't just a convenient story. There is tangible evidence locked within the stars themselves that supports this captivating theory. Astronomers can perform a kind of chemical fingerprinting on starlight. By analyzing the specific wavelengths of light emitted by the stars in NGC 3201, they can determine their chemical composition, the precise amounts of elements like iron, oxygen, and magnesium. What they've found is telling. The stars in this cluster have a distinct chemical signature that sets them apart from the majority of stars that formed native to the Milky Way. This unique metallicity is a powerful clue. strongly suggesting these stars were forged in a different environment, under different conditions, in a galaxy that evolved separately before its dramatic merger with our own. Furthermore, precise measurements of the star's motions within the cluster, their kinematics, add another layer of proof. The internal movement of the stars shows characteristics consistent with clusters known to have been accreted from outside. It's as if the cluster carries not just the memory of its motion, but the architectural blueprint of its original construction. This scenario transforms the cluster from a mere orbital anomaly into a living fossil. It is a cosmic orphan, a surviving remnant of a galaxy that no longer exists, its backward orbit a silent, enduring monument to a cataclysmic event that occurred billions of years ago. This idea forces us to look at the serene night sky with new eyes, to see it not as a static picture, but as a dynamic and sometimes violent tableau, where the ghosts of devoured galaxies continue to dance in the paths of the stars they left behind. But the plot thickens even further when we consider the most extreme gravitational players in the universe, black holes. Their presence adds a thrilling and deeply powerful dimension to this mystery. We're all familiar with the supermassive black holes that lurk at the centers of galaxies, like our own Sagittarius, a star at the heart of the Milky Way. But there's another, more elusive class of these gravitational monsters, intermediate mass black holes. These are the missing link, weighing in at hundreds or even thousands of times the mass of our Sun, and they are theorized to be hiding within the dense cores of some globular clusters. The possibility that one of these could be dwelling inside NGC 3201 opens up a dramatic new line of inquiry. Picture the interior of the cluster for a moment, a densely packed sphere where stars are separated by mere light weeks instead of the light years we're used to. In such a crowded environment, the gravitational influence of a single, incredibly dense object would be profound. If an intermediate mass black hole resides at the cluster's center, it would act as a gravitational anchor, a dominant force around which the entire cluster organizes itself. Over billions of years, complex interactions between this central black hole and the stars swirling around it could have gradually torqued and twisted the cluster's overall path through space. It's a process called dynamical evolution, where the internal dynamics of the cluster don't just affect the stars within it, but can actually alter the trajectory of the entire structure as it orbits the galaxy. The black hole's immense gravity could have acted like a hidden rudder, ever so slowly steering the cluster onto its unusual backward course. There's another, even more cinematic possibility. Perhaps the cluster's path wasn't altered from within, but from without during a perilously close encounter with the supermassive black hole at our galaxy's center. The region around Sagittarius, a star, is a gravitational maelstrom, a place where the laws of physics are stretched to their limit. If, in its long history, NGC 3201 made a close pass by this cosmic behemoth, it would have experienced a gravitational slingshot effect of unimaginable power. This isn't a gentle nudge, it's a violent gravitational assist. The black hole's gravity could have captured the cluster, swung it around in a tight arc, and then flung it back out on a completely new trajectory, potentially even a retrograde one. This process, known as a gravitational scattering event, is a well-understood way to dramatically alter orbits, and it would account for the sheer energy needed to reverse the motion of millions of stars. The challenge and the fascination lies in the fact that both of these black hole scenarios are entirely plausible, yet incredibly difficult to prove. Finding an intermediate mass black hole is like searching for a single invisible needle in a haystack of a million shining stars. Astronomers look for the telltale signs, stars at the very center of the cluster whipping around at inexplicably high speeds, hinting at the presence of a massive, unseen object holding them in its grip. So far, the evidence within NGC 3201 remains inconclusive, making this a compelling lead but not a closed case. Similarly, tracing the cluster's exact orbital path back in time to see if it ever intersected with the galactic center is a monumental task, a calculation fraught with uncertainties over such vast timescales. The black hole hypothesis, in all its forms, injects a dose of high-stakes cosmic drama into the mystery, suggesting that the cluster's backward journey might be the result of a past tango with the most destructive objects in the universe. Yet when we shift our perspective from the force of gravity to the very fabric of reality it warps, we enter a realm where the rules of motion become even more profound. Einstein's revolutionary insight was that gravity isn't just a force pulling between objects, it is the curvature of space-time itself. Mass and energy bend the four-dimensional continuum of the universe, and objects simply follow the straightest possible path through this warped landscape. This means that what we perceive as an orbit isn't a body being pulled in a circle, but rather a star or a cluster tracing a natural groove in the cosmic fabric, like a marble rolling around the inside of a curved bowl. For an object like NGC 3201, moving through the gravitational field of the entire Milky Way, its path is a direct result of the space-time geometry created by all the galaxies mass, both the visible stars and the invisible dark matter. This curvature of space-time doesn't just guide motion, it also warps our perception of time in a phenomenon known as time dilation. In regions of intense gravity, like near a black hole, time itself slows down relative to a distant observer. An astronaut orbiting close to the event horizon would have their clock tick far slower than a clock on Earth. From our vantage point, their movements would appear to be in extreme slow motion, and their orbit might seem to take an impossibly long time to complete. While NGC 3201 is not near such an extreme environment, it is still embedded in the significant gravitational well of our galaxy. Over its immense journey of billions of years, could the cumulative, subtle effects of time dilation have a measurable impact on how we perceive its motion from our specific location in the galaxy? The answer is a fascinating maybe. Relativistic effects are typically tiny on galactic scales and are often dwarfed by the more straightforward gravitational dynamics we've already discussed. However, when we are making precision measurements across tens of thousands of light years, these subtle distortions might not be entirely negligible. The cluster's motion, as we measure it from our solar system's location, is not an absolute truth but a perspective-dependent observation. We are seeing its path through the lens of our own local space-time curvature. If the fabric of space-time between us and the cluster is unevenly warped by the distribution of mass throughout the galaxy, it could potentially introduce a small but systematic shift in our measurements, making a perfectly normal orbit appear slightly more anomalous than it truly is, or perhaps amplifying the peculiarity of an already strange trajectory. This doesn't mean the cluster is literally traveling backward in time, a common science fiction trope that relativity strictly forbids for anything with mass. Instead, it suggests that our interpretation of the data must account for the relativistic framework in which the observation occurs. Our classical Newtonian models of orbital mechanics are incredibly accurate for planning a mission to Pluto, but when applied to the motion of a million-star cluster across the galactic halo over billions of years, they might be missing a layer of nuance. Einstein's equations provide that deeper layer, describing a universe where space and time are interwoven and dynamic. The backward orbit of NGC 3201, therefore, challenges us to ensure that the apparent anomaly isn't partly a trick of the light, or rather, a trick of the bent spacetime through which we are viewing it. It forces a beautiful synthesis where solving a modern astronomical mystery might require the full, profound power of our most advanced physics. But what if the answer lies not in the vast classical forces of gravity, but in the spooky, counterintuitive realm of the incredibly small? When we push past the boundaries of Einstein's relativity and venture into the speculative frontiers of theoretical physics, we find ideas so strange they sound like pure fantasy, yet they are grounded in serious mathematical inquiry. Some physicists propose that the bizarre retrograde motion of NGC 3201 might not be a product of its past at all, but a sign of something far more profound, a fundamental blurring of the lines between gravity and quantum mechanics, or even a faint interaction with realities beyond our own. This line of thinking brings us to the elusive theory of quantum gravity, the long-sought-after holy grail of physics that aims to unite the large-scale world of general relativity with the probabilistic, particle-based rules of quantum mechanics. In the quantum world, particles can be in two places at once. They can tunnel through barriers, and they are connected across vast distances through entanglement. What if these quantum properties don't just apply to tiny particles, but can, on some level, influence massive objects like star clusters? It's a staggering thought. Perhaps the cluster's path isn't a single, defined line through history, but a superposition of many possible paths, a quantum probability cloud on a cosmic scale. From our perspective, we are only observing the one path that has crystallized into reality, which just so happens to be a wildly improbable retrograde orbit. In this view, the anomaly isn't a puzzle to be solved with a past cause, but a statistical fluctuation on a grand, almost impossible scale, a rare roll of the quantum dice that we are fortunate enough to witness. Taking this idea even further, the concept of the multiverse whispers an even more mind-bending possibility. The multiverse theory suggests our universe is just one bubble in a vast, foaming sea of infinite universes, each with its own unique set of physical laws and constants. The boundaries between these parallel realities are typically thought to be impermeable, but what if they aren't perfectly sealed? Could the gravitational influence of a nearby universe, where time might flow backward or the very definition of forward motion is different, be subtly leaking into our own? If so, NGC 3201 might be drifting through a region of space where this inter-universal leakage is slightly stronger, its motion gently nudged by the phantom gravity of a cosmos with inverted physics. Its backward orbit would then be a cosmic landmark, a signpost pointing toward a fracture in the fabric of our reality, a place where the walls between worlds are thin. These ideas are, without a doubt, highly speculative and far from the scientific mainstream. They lack testable predictions and concrete evidence, placing them firmly in the realm of inspired conjecture rather than settled science. But that doesn't make them worthless. On the contrary, they serve a vital purpose. They stretch our imagination to its absolute limits and challenge us to question our most basic assumptions about cause and effect, time and locality. The mystery of this cluster's motion acts as a catalyst, forcing brilliant minds to brainstorm solutions so radical they would otherwise never be considered. It is in this space of wild, untamed speculation that the next great paradigm shift in physics is often born. The retrograde orbit of a million ancient stars becomes more than an astronomical curiosity. It becomes a key, tantalizingly poised to unlock a door to a deeper understanding of reality, inviting us to ask not just how it moves, but what its motion can teach us about the fundamental nature of existence itself. Uncovering the truth behind this cosmic mystery required more than just pointing a telescope at the sky. It demanded a symphony of advanced technology and painstaking analysis. To measure the motion of a cluster 16,000 light-years away with the precision needed to detect its backward orbit, astronomers had to become masters of celestial measurement, employing a powerful trio of observational techniques. The first is astrometry, the ancient science of measuring the positions and movements of stars with incredible accuracy. This is like creating a cosmic map where every star's location is plotted not just in 2 dimensions, but in 3, tracking their subtle shifts across the sky over years and decades. The second technique is spectroscopy, which involves breaking down the light from a star into its constituent colors, or spectrum. When a star is moving toward or away from us, its light waves are compressed or stretched, a phenomenon known as the Doppler effect. This shift in the spectrum reveals the star's radial velocity, its speed directly along our line of sight. By combining astrometry's sideways motion with spectroscopy's toward and away motion, scientists can reconstruct the full, 3-dimensional velocity vector of a star, plotting its exact path through the void. The real game changer, however, has been the advent of dedicated space missions designed to perform these measurements on an industrial scale. The European Space Agency's Gaia spacecraft is the crown jewel of this endeavor. Since its launch in 2013, Gaia has been engaged in an unprecedented cosmic census, meticulously observing over 1 billion stars in our galaxy, not just once, but repeatedly. Its billion-pixel camera measures the positions of each star with an accuracy comparable to pinpointing the diameter of a human hair from 1,000 kilometers away. For a cluster like NGC 3201, Gaia didn't just provide a single snapshot. It provided a detailed movie of its motion, tracking the subtle, collective drift of all its stars against the background of the Milky Way. It was this vast, precise dataset that produced the unequivocal velocity maps, the clear and undeniable evidence that the entire cluster was swimming against the galactic current. But the raw data from Gaia is just the beginning of the story. The journey from those trillions of bits of information to a confident declaration of a retrograde orbit is a long and arduous process of data analysis, a relentless pursuit of accuracy. The first challenge is to correct for a myriad of biases and errors that can creep into the measurements. The light from these distant stars doesn't travel unimpeded to Gaia's lens. It passes through the Earth's atmosphere, which can blur and distort it, and through clouds of interstellar dust, which can redden and dim it. Each of these effects must be meticulously modeled and subtracted from the data. Then there's the instrument itself. No complex machine is perfect. Tiny variations in the spacecraft's temperature, minute shifts in its alignment, or even the slow buildup of microscopic contaminants on its optics can introduce systematic errors. Teams of scientists and engineers spend years developing and refining complex algorithms to identify and remove these instrumental artifacts, ensuring that the final numbers reflect the true motions of the stars and not the quirks of the telescope. The final and perhaps most crucial step is comparison and validation. The measured motion of NGC 3201 isn't accepted as fact in isolation. It is constantly checked and rechecked against other, independent datasets. Ground-based observatories like the Very Large Telescope in Chile perform their own high-resolution spectroscopic studies, providing a separate set of radial velocity measurements that must agree with Gaia's findings. Furthermore, the results are fed into sophisticated computer simulations of the Milky Way. If the cluster's observed motion is real, it should fit within a plausible historical narrative of the galaxy's evolution, perhaps as the result of a past merger or a gravitational encounter. If it doesn't, it could be a sign that a hidden error still lurks in the data. This entire process, from the initial photon of light hitting a sensor to the final, peer-reviewed publication, is a testament to the collaborative and self-correcting nature of modern science. It's a global effort involving thousands of researchers across continents, all working in concert to ensure that when they announce a discovery as extraordinary as a star cluster orbiting backwards, they can do so with absolute confidence. These digital universes, painstakingly built line of code by line of code, are where the abstract dance of gravity is brought to life on a screen. To test the various theories behind NGC 3201's retrograde orbit, astrophysicists turn to a powerful tool known as the N-body simulation. The N stands for the number of particles in this case. Each particle could represent a single star, a bundle of dark matter, or even an entire star cluster. The sheer computational challenge is staggering. Modeling the gravitational pull between just two objects is simple Newtonian physics, but when you add a third, the system becomes chaotic and unpredictable. Now, imagine scaling that up to millions or even billions of interacting particles, all pulling on each other simultaneously across billions of years. Solving this intractable problem requires some of the most powerful supercomputers on the planet, running algorithms that cleverly approximate the forces between distant groups of particles to make the calculations possible. Within these virtual laboratories, scientists become masters of cosmic history, able to rewind and fast-forward time. They start by setting up initial conditions that mirror our best understanding of the early Milky Way, a rotating disk of gas and dust surrounded by a halo of dark matter. Then they introduce a virtual globular cluster, placing it on a prograde orbit, moving in the same direction as the galaxy's spin. This is the default, the expected starting point. Now comes the experimentation. The researchers introduce potential disruptors one by one to see which one can flip the cluster's trajectory. They might program a close flyby of a massive dwarf galaxy, watching as its gravity tugs and distorts the cluster's path. They might seed the dark matter halo with invisible, lumpy clumps and observe if the cumulative gravitational drag from these structures can gradually break and reverse the cluster's motion over eons. They can even simulate a full-scale galactic merger, hurling a small galaxy on a retrograde collision course with the Milky Way to see if its captured cluster retains that backward momentum. The true power of this method lies in the ability to run these scenarios thousands of times, each time slightly adjusting the parameters: the mass of the perturbing object, the closeness of the encounter, the initial velocity of the cluster. It's a massive, automated process of trial and error. The goal is to find a set of conditions that, when the simulation is run, produces a virtual cluster that ends up looking and moving exactly like the real NGC 3201 we observe today. When a simulation finally matches reality, it's a eureka moment. It doesn't just provide a plausible story, it offers a statistically validated pathway, a most probable history that can be studied in exquisite detail. These digital experiments have shown that retrograde orbits, while rare, are not impossible. They can emerge naturally from the chaotic and violent environment of a growing galaxy, a testament to the dynamic and often turbulent processes that shape our universe. The simulations act as a crucial bridge, connecting a single, strange observation in the present to a rich tapestry of potential past events, allowing us to virtually witness the dramatic encounter that may have sent a million stars spinning the wrong way. While NGC 3201 captivates us with its backward journey, it is far from the only globular cluster in the Milky Way that refuses to follow the standard script. The galaxy is dotted with other ancient stellar systems that exhibit their own peculiarities, each one a unique piece of the puzzle of galactic evolution. By placing NGC 3201 side by side with these other anomalous clusters, astronomers can perform a kind of cosmic comparative anatomy, identifying which traits are unique and which might be symptoms of a broader, shared history. This method transforms a single mystery into a rich dataset, allowing scientists to separate the truly extraordinary from the merely unusual. A prime example of another cosmic enigma is the magnificent Omega Centauri, the largest and brightest globular cluster orbiting our galaxy. Visible to the naked eye as a faint, fuzzy star, it has been known since antiquity, but its true nature is anything but simple. Unlike typical globular clusters, which contain stars of a similar age and composition, Omega Centauri is a stellar mosaic. Its millions of stars show a stunning diversity in their metal content and ages, spanning a range of over 2 billion years. This suggests it was not born in a single, rapid burst of star formation, but had a much more complex and prolonged genesis. For a long time, the leading theory has been that Omega Centauri is not a genuine globular cluster at all, but the stripped-down core of a dwarf galaxy that was devoured by the Milky Way long ago. Its immense gravity held it together while the rest of its parent galaxy was torn apart, leaving behind a massive, chaotic relic of that ancient collision. Its motion, while not retrograde, is still highly energetic and complex, fitting the profile of an object with a violent past. Then there are clusters like M71 and Palomar 5, which tell different stories altogether. M71 is unusual because it resembles both a loose globular cluster and a very dense open cluster, blurring the line between the two classifications and suggesting that the family of star clusters might have more variety than we once thought. Palomar 5, on the other hand, is famous for its fragility. It is being actively torn apart by the Milky Way's gravity, leaving behind spectacular tidal tails of stars that stream across the sky like celestial ribbon. This process of tidal disruption is a fate that may await many clusters, and studying Palomar 5 gives us a front-row seat to the destructive forces that shape the galactic halo. Its eventual dissolution will scatter its stars into the general population of the Milky Way, erasing its identity but adding to the galaxy's rich stellar tapestry. When we compare NGC 3201 to these other outliers, its retrograde orbit stands out as a particularly rare signature. The diverse chemical makeup of Omega Centauri points to a unique origin story. The ambiguous nature of M71 hints at a different formation pathway, and the disintegration of Palomar 5 illustrates a common destiny. But a backward orbit is different. It is a powerful and lasting dynamical imprint, a clear signal of a specific type of gravitational interaction or capture event that happened long ago. This comparative analysis allows researchers to ask more precise questions. Is a retrograde orbit always linked to a specific chemical fingerprint, like the one suggesting an extragalactic origin for NGC 3201? Does it only occur in clusters of a certain mass or density that can survive such a dramatic gravitational encounter? By building this catalog of anomalies, scientists can start to see which characteristics tend to travel together and which are independent, slowly decoding the different evolutionary paths these ancient systems can take. This holistic view reveals that the population of globular clusters orbiting the Milky Way is not a monolithic group of identical objects, but a diverse collection of survivors, each with its own story to tell. Some are pristine relics from the Milky Way's own birth, others are captured invaders from alien galaxies, and a few, like NGC 3201, are rebels that move to the beat of their own drum. Their combined histories write a far more thrilling and violent biography for our galaxy than a quiet, isolated evolution. They are testament to a past filled with collisions, mergers, and close calls, a dynamic history where the gravity of dark matter clumps and dwarf galaxies continually stirred the pot, leaving behind a zoo of exotic astronomical objects for us to discover and decipher. This single cluster's strange path does far more than just present an interesting puzzle. It forces us to reconsider the entire life story of our galaxy and how it grew into the majestic spiral we see today. For decades, the prevailing model of galactic evolution was one of relatively quiet and isolated growth. In this view, the Milky Way formed mostly from a single, collapsing cloud of primordial gas, with its stars and clusters spinning in an orderly, unified direction, much like the planets in our solar system. Globular clusters were seen as the faithful, ancient tracers of this calm and steady process, their orbits mapping out the serene gravitational field of a well-behaved galaxy. The discovery of a massive cluster moving in clear defiance of this rotation is like finding a single gear spinning backward in a perfectly tuned watch. It's a glaring sign that the internal mechanism is far more complex than we ever assumed. This backward motion strongly suggests that our galaxy's history was not one of peaceful solitude, but rather a violent and chaotic series of acquisitions. It points to a past filled with dramatic mergers and relentless gravitational interactions with smaller galaxies and dark matter substructures. If one cluster can be flipped onto a retrograde path, it implies that such disruptive events were not rare, freak occurrences, but were common enough to leave a lasting mark on the orbital architecture of our galactic halo. This transforms our image of the Milky Way from a solitary island universe into something more akin to a bustling cosmic metropolis, built over billions of years through a process of constant construction, demolition, and renovation, with entire neighborhoods of stars being imported from elsewhere. The implications of this are profound for predicting the future of our galaxy. Our current models for the ultimate fate of the Milky Way, including its impending collision with the Andromeda Galaxy, are based on simulations that incorporate certain assumptions about the mass distribution and gravitational field of our own galaxy. If that gravitational field is significantly lumpier and more disordered than we thought, shaped by numerous past mergers and populated by numerous objects on wild, unexpected orbits, then those predictions might need a serious revision. The presence of massive objects on retrograde paths could influence the dynamics of the entire galactic halo, potentially affecting the stability of other clusters, or even the rate at which the Milky Way consumes smaller satellite galaxies. Ultimately, this one cluster's anomalous behavior acts as a key that unlocks a new chapter in the story of structure formation. It provides direct, observable evidence that the process of building a galaxy is messy, dynamic, and far from finished. By studying its path, astronomers are not just solving a single mystery, they are calibrating the entire narrative of cosmic evolution. They are learning that the serene pinwheel of the Milky Way we see today is merely a snapshot in a long, violent, and spectacularly beautiful movie, a film in which retrograde orbits are not mistakes in the script, but crucial plot twists that reveal the true, dramatic story of how a galaxy is made. Word of the discovery spread through the astrophysics community not with a whisper, but with the energy of a supernova. When the team's paper was published, its title, though technical, hinted at the extraordinary finding within, and it didn't take long for science communicators and journalists to distill its complex data into a captivating headline: Astronomers discover star cluster orbiting backwards. That single phrase, particularly the notion of something moving backwards, immediately captured the public's imagination. It wasn't just a story for academic journals. It was a concept that felt pulled from the pages of a science fiction novel, and it quickly ignited a firestorm of fascination across the globe. Online forums buzzed with speculation, social media feeds filled with artistic renditions of the rebellious cluster, and news segments tried to explain the physics to a lay audience, often leaning into the more poetic and mysterious angle of defying time itself. This public captivation revealed a deep, almost universal human yearning for cosmic wonder, a reminder that even in our advanced technological age, the universe still holds the power to astonish us with its sheer strangeness. Within the halls of academia, the reaction was a potent mix of excitement and intense, rigorous skepticism. At conferences and in university departments, the finding became a central topic of discussion, not as settled fact, but as a compelling puzzle to be solved. Seasoned astronomers, while impressed by the quality of the Gaia data, immediately began probing for potential weaknesses in the analysis. Could there be an unaccounted for systematic error in the measurements? Was the interpretation of the cluster's motion too simplistic, perhaps not fully considering the complex gravitational field of the Milky Way's halo? This healthy, critical dialogue is the very engine of scientific progress. Researchers from different subfields, dynamicists, dark matter experts, galactic archaeologists, each brought their unique toolkit to the problem. Papers began to appear, not just presenting the original data, but offering alternative models and competing explanations, each one trying to weave a more coherent story for the cluster's past. This wasn't a conflict but a collaboration through debate, a collective effort to test an extraordinary claim until only the most robust truth remained. The resonance of this mystery for both the public and the scientists taps into something far deeper than mere intellectual curiosity. For the average person, the idea of a backwards orbit touches on foundational questions about the nature of time and our place in the cosmos. It challenges our everyday, linear perception of time in a way that feels both thrilling and disorienting. It's a tangible piece of evidence that the universe operates by rules that are profoundly alien to our earthly experience, and this evokes a sense of awe that is both humbling and inspiring. It makes the vast, abstract cosmos feel intimately strange and personally fascinating. For the scientists, the allure is equally powerful but framed within a different context. A clear anomaly like this is not a nuisance, it is a precious gift. A universe that behaves exactly as predicted offers no new paths to discovery. It is the outliers, the data points that stubbornly refuse to fit the existing models, that force a paradigm shift. NGC 3201's retrograde motion is such a data point. It represents a potential key, a key that could unlock a better understanding of dark matter distribution, of galactic merger histories, or even of gravitational physics itself. The mystery resonates because it represents a frontier, a blank spot on the map that promises not just an answer, but the possibility of entirely new questions. This ongoing dialogue, conducted in published papers and conference halls and amplified by public wonder, ensures that this celestial rebel won't just be a passing curiosity, but a catalyst for a deeper exploration of the cosmic order. Yet as we reach for the stars and decode the universe's deepest secrets, we must pause to consider the profound ethical dimension of this quest. Unlike fields such as medicine or genetics, where research can directly impact human lives with immediate consequences, cosmic exploration might seem ethically neutral, a pure pursuit of knowledge for its own sake. But this perspective is deceptively narrow. Every time we point our telescopes toward the heavens and unravel a new mystery, we are indirectly making a statement about our values, our priorities, and our place in the cosmos. The act of seeking to understand something as wondrous and strange as a cluster orbiting backwards isn't just a technical challenge. It's a philosophical endeavor that forces us to reflect on why we explore in the first place and what we hope to gain from it. One of the core ethical considerations is the sheer allocation of resources. Building spacecraft like Gaia, maintaining powerful ground-based observatories, and funding the teams of scientists who analyze the data requires a significant investment of public money and human intellect. In a world grappling with poverty, disease, and climate change, some might rightly question whether peering at distant star clusters is a responsible use of our collective effort. The defense, and indeed the profound value of this work, lies in its long-term foundational impact. The technologies developed for astronomy often spin off into societal benefits: the CCDs in our digital cameras, the algorithms that enhance medical imaging, and the advancements in data processing that power modern computing all have roots in our drive to understand the universe. More importantly, this fundamental research feeds the human spirit. It provides a sense of perspective, humility, and awe that is essential for a thriving society. It reminds us that we are part of something vastly larger than our daily conflicts, fostering a global identity and a sense of shared wonder that can, in its own way, inspire solutions to earthly problems. Furthermore, the knowledge we gain carries its own weight of responsibility. Discovering that our galaxy was built through violent collisions and acquisitions challenges anthropocentric views of a universe designed for us. It can be a humbling, even unsettling realization. How do we handle knowledge that fundamentally alters our perception of reality? The scientific community has a duty to communicate these discoveries with honesty and transparency, but also with care. We must avoid sensationalism that could lead to public misunderstanding, while simultaneously embracing the awe that such discoveries rightly inspire. This balancing act between wonder and wisdom requires a commitment to clear, accessible education. It means sharing the story of NGC 3201 not as a frightening anomaly, but as an exciting chapter in our ongoing cosmic story, one that invites everyone to be part of the journey of discovery. This pursuit also connects to a deeper, almost spiritual ethical principle, the principle of cosmic stewardship. While we are not yet capable of affecting distant star clusters, our growing understanding of the universe's fragility and interconnectedness reflects back on our responsibility toward our own planet. Studying the ancient, silent dance of globular clusters can instill a powerful sense of care for the delicate, vibrant world we inhabit. It underscores that Earth is a rare and precious oasis in a vast and mostly inhospitable cosmos, making its preservation not just an environmental goal, but a cosmic imperative. The ethics of cosmic research, therefore, are not about navigating immediate moral dilemmas, but about cultivating a mindset of curiosity tempered with humility, ambition guided by responsibility, and wonder paired with a deep respect for the intricate tapestry of existence we are only just beginning to comprehend. The quest to unravel the secret of this backward orbiting cluster is far from over. In fact, we are standing on the threshold of a new golden age of discovery, powered by a wave of next-generation observatories that will see the cosmos with unprecedented clarity. Leading this charge is the James Webb Space Telescope, an engineering marvel that operates not in visible light, but in the infrared spectrum. This is a game-changer for studying a cluster like NGC 3201. Infrared light pierces through the veils of interstellar dust that can obscure and redden starlight, allowing Webb to see the cluster's individual stars with stunning crispness. Imagine being able to not just see the cluster as a fuzzy ball of light, but to resolve thousands of its individual ancient suns, measuring their brightness and color with exquisite precision. This will allow astronomers to create a far more detailed map of the cluster's internal structure and to precisely measure the motions of stars within it, searching for the telltale signs of a central, intermediate mass black hole whose gravitational influence could have helped steer the cluster on its unusual path. Simultaneously, here on Earth, the Vera C. Rubin Observatory is preparing to undertake a 10-year survey of the entire southern sky, a project that will utterly transform our view of the dynamic universe. Unlike telescopes that focus on a single object, Rubin will scan the entire sky every few nights, creating an enormous time-lapse movie of the cosmos. For NGC 3201, this means something incredible. We will no longer have a static snapshot of its motion. Instead, we will be able to watch its trajectory evolve over time with incredible accuracy, measuring tiny changes in its path that could reveal the subtle, ongoing gravitational tugs from dark matter clumps or other invisible structures it might be passing near. This relentless monitoring will provide a dynamic, real-time chart of its journey, offering clues about the forces acting upon it right now. The data from these powerful new eyes will be used to test the competing theories with a level of rigor previously impossible. For instance, the galactic cannibalism model predicts that the stars within NGC 3201 should have a specific chemical fingerprint, distinct from native Milky Way stars. Webb's powerful spectrographs will be able to analyze the chemical composition of hundreds of individual stars within the cluster, not just as a whole. If they all share a unique and consistent alien signature, it would be powerful evidence that the entire cluster was indeed captured from a devoured dwarf galaxy. Conversely, if the stars show a mix of compositions, it might point toward a different history, perhaps one involving a dramatic gravitational encounter that stirred the cluster's interior. This monumental effort is a truly global endeavor. The data from Webb, Rubin, and other facilities like the European Southern Observatory's extremely large telescope will be pooled in international archives, accessible to scientists from every corner of the world. This collaborative spirit means the mystery won't be solved by a single lone genius in an isolated lab, but by a diverse, worldwide community of astronomers, data scientists, and theorists, all bringing their unique expertise and perspectives to the same rich dataset. They will run increasingly sophisticated computer simulations, feeding them the new, precise data to see which simulated past, be it a galactic merger, a dark matter interaction, or a black hole encounter, most perfectly recreates the cluster we see today. This forward-looking approach, fueled by collaboration and cutting-edge technology, guarantees that the story of this celestial rebel is still being written, and its next chapters promise to be the most revealing yet. The mystery of a star cluster moving against the galactic current is more than just an astronomical puzzle. It's a powerful catalyst for curiosity, a perfect gateway to inspire the next generation of scientists, engineers, and dreamers. Imagine a high school physics class where students might typically groan at the abstract formulas of orbital mechanics. Now, reframe that lesson around the enigma of NGC 3201. Suddenly, it's not about solving for velocity on a worksheet. It's about becoming a cosmic detective. Students can be given the same data that baffled professional astronomers and tasked with developing their own theories. Was it a dark matter encounter, a galactic merger? This hands-on, inquiry-based approach transforms learning from passive reception into an active, thrilling investigation, mirroring the actual scientific process of hypothesis, testing, and revision. It shows them that science isn't a static set of facts in a textbook, but a dynamic, living process of discovery where unanswered questions are the most exciting part of all. This story is also a brilliant tool for teaching the interconnected nature of scientific disciplines. To truly grasp the possibilities behind the cluster's motion, a student must draw upon physics for gravity and motion, chemistry for stellar composition, geology for understanding planetary formation, and even computer science for the simulations that model its history. It shatters the artificial boundaries between subjects, demonstrating how real-world problems require a unified, interdisciplinary approach. Furthermore, the topic naturally introduces advanced concepts like relativity and dark matter in a tangible, accessible way. Instead of presenting Einstein's theories as impenetrable math, educators can use the cluster's path to discuss how gravity warps spacetime, making these profound ideas feel concrete and relevant. Planetariums and science centers can take this even further, creating immersive visualizations that allow visitors to literally fly alongside the cluster on its backward journey, fostering a deep, emotional connection to the science. The ultimate goal of this educational outreach is to democratize wonder. By breaking down these complex cosmic mysteries into engaging narratives, we make science accessible and exciting for everyone, regardless of their background or prior knowledge. It sends a critical message that the universe is not just for experts in ivory towers. It is a shared human inheritance, and everyone is invited to participate in its exploration. This is how we ignite a lifelong passion for learning. A child who is captivated by the story of a rebellious star cluster today might be the astronomer who solves the mystery tomorrow, or the engineer who designs the next great space telescope, or simply an informed citizen who looks up at the night sky with a deeper sense of awe and understanding. By sharing these stories, we aren't just teaching facts, we are nurturing the innate human curiosity that drives all progress, ensuring that the future of discovery is in passionate and capable hands. This backward orbit, this defiance of galactic expectation, forces us to confront questions that have haunted philosophers for millennia. We perceive time as a river, flowing inexorably in one direction from the past through the present and into the future. This is the arrow of time, a concept deeply embedded not just in physics, but in our very consciousness. We remember the past, we anticipate the future, and this linear progression feels as fundamental as gravity itself. Yet here we have a physical system, a massive cluster of stars, whose motion seems to metaphorically poke a hole in that comfortable certainty. It doesn't literally travel back in time, of course, but its retrograde path against the cosmic grain acts as a powerful symbol, challenging the very notion of a single, universal flow of events. It whispers that on a grand cosmic scale, the universe might not care about our earthly perceptions of before and after. This immediately brushes against profound questions of causality, the principle that cause must precede effect. It's the bedrock of not just science but of human experience. We turn a key to start a car, we plant a seed to grow a tree. But what if the universe allows for conditions where THI's Chinese letter feels less rigid? The cluster's motion, shaped by gravitational interactions over billions of years, is the effect of ancient causes that are now lost to us. Its present state is a palimpsest of its entire history, a history that may include violent mergers or invisible dark matter encounters. This deep interconnectedness suggests that the present moment is not a clean, discrete point on a line, but a rich tapestry woven from countless threads of past events, some of which might have their own different directional biases. The cluster's path asks us to consider if the arrow of time is a local phenomenon, perhaps even an emergent property of increasing entropy in our corner of the universe, rather than a fundamental rule written into the fabric of spacetime everywhere. This naturally leads to more personal, human-centric philosophical dilemmas about free will and destiny. If the motions of million star clusters are dictated by the immutable laws of gravity playing out over eons, where does that leave our own sense of agency? Are our lives on some unimaginably complex level simply the playing out of a cosmic script written at the dawn of time, with every choice predetermined by the initial conditions of the Big Bang and the subsequent gravitational dance of matter. The cluster's path, seemingly bizarre to us, was likely an inevitable outcome of the specific conditions and forces it encountered. Or does its uniqueness, its outlier status, suggest that even within a universe governed by physical laws, there is room for genuine novelty, for unexpected outcomes that are not preordained? Perhaps its journey is a testament to the role of chance encounters in a chaotic cosmos, a concept that leaves the door open for unpredictability and thus, by analogy, for free will in our own lives. Ultimately, the greatest philosophical implication is the challenge to our perception of reality itself. We trust our senses and our instruments to give us an accurate picture of the world. We see the cluster moving backwards and we accept that data as real, but our understanding of that reality is filtered through the limited models our brains can construct. The cluster forces us to admit that our models are incomplete. Our classical intuition about motion and time is a useful illusion for navigating our everyday world, but it breaks down at the extremes of the cosmos, just as it breaks down at the quantum scale. This humble acknowledgement is the very heart of the scientific and philosophical spirit. The mystery of this ancient cluster isn't just an astronomical problem to be solved. It is a mirror held up to our own minds, revealing the boundaries of our current understanding and inviting us to imagine a reality far stranger and more wonderful than we have yet conceived. Long before telescopes and satellites, human eyes were fixed on the heavens, tracing the wanderings of planets against the backdrop of fixed stars. And when those planets did the unexpected, like Mars, Jupiter, or Saturn, periodically halting their eastward journey and looping backward in a mysterious retrograde dance, our ancestors did not see a simple orbital mechanic. They perceived intention, a message written in the sky by the gods themselves. In ancient Mesopotamia, these backward loops were meticulously recorded by priest astronomers, who saw them as celestial omens, divine warnings meant to foretell the fate of kings and empires. The very word planet comes from the Greek planetes, meaning wanderer, because these objects moved to their own enigmatic rhythm, separate from the orderly procession of the constellations. They were seen as living entities, gods on the move, and their retrograde motion was a powerful, often fearsome, act of communication. This deep-seated human instinct to ascribe meaning to celestial motion is a thread that connects the Babylonians to our modern mystery. While we now understand the science behind a planet's retrograde loop, an elegant illusion created as Earth overtakes a slower orbiting outer planet, the emotional resonance remains. The discovery of NGC 3201's genuine retrograde orbit taps directly into that ancient well of wonder. It reawakens that primal feeling that the cosmos is not just a clockwork mechanism, but a place of deep mystery and potential significance. Our tools have changed from clay tablets to space telescopes, but the fundamental human response, a mix of awe, curiosity, and a desire to decipher the message, is a timeless constant, linking the astrologers of old with the astrophysicists of today. It's a thrilling exercise of the imagination to wonder what myths and legends might have blossomed had the keen-eyed astronomers of antiquity been able to perceive this faint, backward gliding cluster. Without the context of a galaxy or any concept of its scale, NGC 3201 would have appeared as a faint, nebulous smudge, a ghostly patch of light. But its motion, if it could have been tracked over generations, would have marked it as utterly unique. Perhaps the Polynesian navigators, who used the stars to guide their incredible voyages across the Pacific, would have seen it as a celestial canoe carrying the souls of great chiefs against the current of the Sky River, a sign of immense spiritual power and a harbinger of great change. In the Norse tradition, it might have been interpreted as one of the runaway sparks from Muspelheim, the realm of fire, hurtling backward in a defiant act against the ordered cosmos, a portent of Ragnarök. The ancient Greeks, with their rich pantheon, might have woven an entire epic around it. They could have seen it as the scattered flock of the golden-fleeced ram, forever fleeing backward from the grasp of the hero Jason and his Argonauts, a permanent reminder of a prize that could never be truly captured. Or perhaps it would have been the funeral bier of a fallen titan, pulled by black horses in a perpetual, mournful retrograde procession around the pole star, an eternal monument to a lost age of giants. These are not just fanciful stories, they are a testament to the human need for narrative. We use stories to make sense of the world, to contextualize the unknown, and to find our place within a vast and often incomprehensible universe. The science gives us the how, but the mythology points to the why we care, why we look up, and why a cluster of ancient stars moving the wrong way feels so deeply significant on a human level. This beautiful intersection of empirical discovery and cultural storytelling is where science finds its deepest connection with the public. By acknowledging these mythological echoes, we don't diminish the scientific achievement, we enrich it. We build a bridge between the cold, hard data and the warm, beating heart of human curiosity. It allows everyone, regardless of their scientific background, to find a point of entry into the mystery. The story of NGC 3201 becomes more than a physics problem. It becomes part of a continuum, the latest chapter in humanity's oldest and most ongoing story, our eternal conversation with the stars. While the dance of a distant star cluster might seem like abstract physics with no bearing on our daily lives, the principles we uncover by studying its strange motion have incredibly practical and down-to-earth applications. The same fundamental laws of orbital mechanics that govern NGC 3201's retrograde path are the very same rules we use to manage the intricate network of technology we've placed in the space around our planet. Every time you use your smartphone's GPS to navigate to a new location, you are directly benefiting from our deep understanding of how gravity shapes trajectories. The global positioning system is a constellation of satellites, each one in a precise, carefully calculated orbit, constantly broadcasting signals that report its exact location and the exact time. Your phone receives these signals, and by calculating the tiny differences in how long each signal took to arrive, it can triangulate your position on Earth with astonishing accuracy. But these satellites don't just stay put. They are constantly moving, and their orbits are subtly perturbed by the very forces we've been discussing: the uneven gravitational pull of the Earth, which isn't a perfect sphere, the gentle but persistent push of solar radiation, and even the gravitational influence of the Moon and Sun. If we didn't have incredibly sophisticated models of orbital mechanics, born from the same physics that explains star clusters, the GPS signals would drift into uselessness within a matter of hours. The math used to correct for these perturbations and keep your Maps app accurate is a direct descendant of the calculations used to trace the path of NGC 3201. This celestial mechanics is what ensures delivery drivers find your house, airplanes cross oceans safely, and financial networks can timestamp transactions to the microsecond. Beyond navigation, this knowledge is our first and most important line of defense against the growing threat of space debris. The region around Earth is no longer a pristine void. It's a celestial junkyard filled with millions of pieces of defunct satellites, spent rocket boosters, and fragments from past collisions, all whizzing around the planet at speeds exceeding 17,000 miles per hour. A collision with a piece of debris the size of a paint chip can have the energy of a hand grenade, capable of crippling a functioning satellite or the International Space Station. Predicting the paths of this debris is a monumental task in orbital mechanics. Just like modeling the gravitational influences on a star cluster, it requires tracking countless objects, calculating how their orbits are being altered by atmospheric drag and other forces, and forecasting potential close approaches or collisions. The techniques developed to understand the chaotic and dynamic environment of a globular cluster are directly applicable to managing this hazard. By applying these principles, organizations like the United States Space Force and private space traffic management companies can issue collision warnings, allowing satellite operators to perform evasive maneuvers. This protects critical infrastructure, from weather forecasting and climate monitoring satellites to the telecommunications networks that power the global internet. The same physics that explains a billion-year-old anomaly is actively used to safeguard the billion-dollar assets we rely on for modern life. Studying the cosmos doesn't just satisfy our curiosity. It provides us with the essential tools to operate safely and sustainably in our own immediate orbital environment, turning theoretical mysteries into practical, everyday safeguards. The phrase "orbiting backwards through time" has a certain poetic ring to it, one that easily conjures up images from science fiction, of starships jumping into hyperspace or heroes twisting the fabric of chronology itself. It's a captivating idea, but it's crucial to pull back the curtain and understand what this really means, because the truth is both more ordinary and, in its own way, far more extraordinary. This cluster is not literally traveling into the past. There are no stars here violating causality or moving backward along the timeline of the universe. What we are observing is a phenomenon of relative motion and perspective, a cosmic dance dictated entirely by gravity. Think of it like this. Imagine you're driving on a vast, multi-lane highway where almost every car is moving in one direction. Now picture one car, a massive, ancient vehicle moving steadily in the opposite direction in its own lane. That car isn't defying the laws of physics or moving backwards in time. It's just going the wrong way on the highway. Its motion is relative to the flow of all the other cars. That's precisely what's happening with NGC 3201. It is orbiting the center of our galaxy in a direction that is opposite, or retrograde, to the rotation of the vast majority of the Milky Way's other components. Its clock is ticking forward just like ours. It is moving into the future alongside us, but its path through space is simply oriented differently relative to the galactic norm. The through time part of the description is a powerful metaphor for its ancient age and unique trajectory, not a statement of literal time reversal. This distinction isn't just academic nitpicking, it's the very heart of effective science communication. When a complex idea like this captures the public imagination, it creates a precious opportunity for education and engagement. But if that engagement is built on a foundation of misunderstanding, the entire opportunity is lost. If people walk away believing astronomers have discovered actual time travel, they've been entertained by a fantasy, not enlightened by a scientific reality. The real story of gravitational dynamics, galactic cannibalism, and dark matter is arguably more thrilling because it is Chinese letter. It's a story about how our universe actually works, not how we might wish it worked in our fantasies. By clearly separating the scientific fact from science fiction, we do more than just preserve accuracy. We invite everyone into the genuine awe of discovery. We show that the true universe, in all its complex, law-abiding glory, is more surprising and magnificent than any fiction we could invent. Furthermore, in an age where misinformation can spread faster than light across social media, upholding this clarity is a matter of intellectual integrity. Cosmic mysteries, with their inherent grandeur, are particularly vulnerable to being co-opted by pseudoscientific theories. A misunderstanding about backwards time travel could easily be seized upon and twisted to promote everything from faulty cosmology to outright conspiracy theories. By preemptively and clearly debunking the misconception, scientists and educators build a buffer of public awareness. They arm people with the critical thinking skills needed to evaluate sensational claims, not just about astronomy, but about all areas of science. It fosters a public that is curious yet skeptical, enthusiastic yet discerning, a public that is better equipped to navigate a world filled with complex information. Ultimately, this commitment to clarity is a form of respect for the audience's intelligence and respect for the scientific process itself. It acknowledges that people are capable of understanding nuanced concepts without needing to dress them in magical clothing. The motion of this ancient cluster is a profound puzzle that challenges our models and deepens our understanding of gravity's story. That story deserves to be told with honesty and precision, allowing its true significance to shine through and inspiring our authentic, lasting wonder for the real mechanics of our incredible cosmos. To truly grasp the full implications of this celestial rebellion, we must move beyond the traditional boundaries of astronomy and embrace a truly interdisciplinary approach. The mystery of NGC 3201 is not a puzzle that can be solved by astrophysicists alone. It demands a collaborative symphony of expertise from across the entire spectrum of human knowledge. This is where the most exciting breakthroughs in modern science are born, at the vibrant intersections between established fields, where different ways of thinking collide and create something entirely new. Consider the role of advanced mathematics, the fundamental language of the cosmos. While astrophysicists provide the physical questions, it is mathematicians who develop the complex formalisms needed to describe the chaotic dance of gravitational interactions. They work with non-linear dynamics and chaos theory to model how a system as sensitive as a star cluster can be dramatically altered by a tiny perturbation over immense timescales. Their equations provide the rigorous framework that turns a qualitative idea, like a close encounter could flip its orbit, into a quantitative, testable prediction. Without these mathematical tools, our understanding would remain purely descriptive, trapped in the realm of appealing stories rather than rigorous science. Equally indispensable are the contributions of computer science and data analytics. The sheer volume of data from missions like Gaia is so colossal that traditional analysis is impossible. It falls to data scientists to design and implement sophisticated machine learning algorithms that can sift through the observations of over 1 billion stars to identify subtle patterns and correlations that would escape the human eye. These algorithms can classify types of stellar motion, filter out noise, and even predict where to look next for similar anomalies. Furthermore, the creation of the N-body simulations themselves is a monumental feat of computational science, requiring ingenious coding to efficiently calculate the gravitational forces between millions of particles. The powerful supercomputers that run these codes are the digital laboratories where cosmic history is replayed, and they are built and programmed by teams of engineers and software experts whose skills are as critical to the discovery process as the telescope that collected the starlight in the first place. Perhaps most surprisingly, this investigation also benefits from the insights of philosophy. This might seem like an abstract addition, but philosophers of science play a crucial role in examining the underlying assumptions and methodologies that guide the research. They help scrutinize the very concepts at play. What do we really mean by time or causality in this context? They encourage scientists to consider epistemological questions. How do we know what we know about this cluster? Are we limited by our own terrestrial perspective? This philosophical lens ensures that the scientific process remains self-aware and critically examined, preventing researchers from becoming trapped within a single paradigm and encouraging the kind of creative, out-of-the-box thinking that such a profound mystery demands. This collaborative model is the new frontier of discovery. A cosmologist might develop a theory about dark matter perturbations. A mathematician will translate that into workable equations. A computer scientist will code it into a simulation. And a philosopher will help assess the logical coherence of the entire endeavor. Each specialist speaks a different language, but together they are writing a new, unified story about the universe. The retrograde orbit of this ancient cluster is more than an astronomical oddity. It is a catalyst for cooperation, proving that the most intractable puzzles of the cosmos can only be solved by harnessing the combined intelligence of all our intellectual traditions, from the most concrete equations to the most abstract contemplations. And this incredible endeavor, this global pursuit to map our galaxy and solve its deepest mysteries, isn't just for professional astronomers with access to giant telescopes. Some of the most important discoveries are now being made by people just like you from the comfort of their own homes. This is the world of citizen science, a revolutionary movement that is throwing open the doors of research and inviting everyone to become a cosmic explorer. When a mission like Gaia sends back its raw data on billions of stars, that information is a treasure trove, but it's also an overwhelming deluge. There are simply more stars and more subtle patterns in that data than any single team of researchers could ever hope to analyze on their own. This is where the collective power of human curiosity becomes an invaluable scientific instrument. Online platforms like Zooniverse have created a beautiful bridge between the public and cutting-edge research. On these websites, astronomers can upload their data and design simple, intuitive tasks that anyone can learn to do in a few minutes. Imagine logging on and being presented with real images of star fields from a major observatory. Your task might be to look at the motions of specific stars over several images and help classify their movement, or to identify the subtle patterns that might indicate a gravitational lens or a previously unknown binary system. For a project focused on NGC 3201, you could be helping to trace the proper motions of its individual stars across the Gaia data, contributing directly to building a more precise map of its retrograde trajectory. Each classification you make is a tiny piece of a massive, crowdsourced puzzle. The magic of this approach lies in the unique strengths of the human brain. While computers are excellent at processing vast amounts of data quickly, they can struggle with pattern recognition when those patterns are faint, complex, or entirely unexpected. The human eye, guided by intuition and curiosity, is exceptionally good at spotting anomalies, the one thing that looks slightly out of place, the weird motion that doesn't fit the established model. It was a citizen scientist poring over data from NASA Kepler telescope who famously identified the strange, irregular dimming of a star now known as Tabby's star, a discovery that led to years of scientific debate and investigation. By empowering a global army of volunteers to sift through the data, scientists massively expand their ability to find these rare and serendipitous needles in the cosmic haystack. This engagement does more than just accelerate the pace of discovery. It fundamentally transforms the relationship between science and society. When you spend an evening classifying star motions, you are no longer a passive consumer of scientific news. you are an active participant in the process of creating that knowledge. You develop a personal stake in the outcome, a connection to the mystery of NGC 3201 that is far deeper than simply reading about it in an article. This fosters a powerful sense of community and shared purpose, connecting people from all walks of life across the globe through a common goal of exploration. It democratizes research, proving that the drive to understand the universe is a universal human trait, not a privilege reserved for those with a PhD. Every click, every classification, is a vote of confidence in the human spirit of inquiry, and a testament to the idea that some of the biggest questions can only be answered when we all look up together. Yet, pondering the existence of these ancient clusters, these celestial cities of stars that have burned for longer than our planet has even existed, does something profound to our perspective. It invites a deep and humbling sense of scale. We learn about environments so extreme, so alien, and so utterly inhospitable to life as we know it, worlds of crushing gravity, searing radiation, and vacuum, that by stark contrast our own planet transforms in our eyes. It is no longer just our home, it is a breathtakingly rare oasis, a delicate, shimmering bubble of blue and green and white, teeming with a complexity of life that we have yet to find anywhere else in the vast, silent cosmos. This realization, born from cosmic exploration, is perhaps the most powerful argument for environmental stewardship we could ever have. This cosmic perspective fosters a powerful sense of planetary humility. We are not the center of the universe, we are a fragile part of an immense and mostly unforgiving system. Understanding that our galaxy contains billions of stars, many with their own planets, and that our galaxy is just one of billions more, shrinks our earthly conflicts and territorial disputes into a sobering new context. It doesn't make our problems less important, but it frames them within a much larger picture. The question shifts from whether we can dominate our environment to whether we can learn to live in harmony with it, recognizing that this single, fragile world is all we have. The same ingenuity that allows us to calculate the orbit of a distant star cluster is the same ingenuity we must now apply to solving the challenges of sustainable energy, resource management, and conservation right here at home. There is a beautiful and practical synergy between the two endeavors. The technology developed to explore the cosmos consistently provides us with the tools to better understand and protect our planet. The satellites we launch to study distant nebulae are the very same platforms we use to monitor global weather patterns, track the melting of polar ice caps, and measure the health of forests and oceans from space. The extreme efficiency required for life support systems on the International Space Station inspires innovations in closed-loop recycling and water purification that can be applied in communities around the world. The study of other planets like Venus with its runaway greenhouse effect or Mars with its lost oceans serves as a stark warning system, showing us potential futures we must work to avoid. Ultimately, gazing at the stars doesn't encourage us to abandon Earth in search of something better. It compels us to care for it with renewed vigor and reverence. The lesson from the cosmos is one of profound responsibility. It teaches us that we are not just citizens of a nation, but citizens of a planet, a crew on a spaceship hurtling through the void. We are all astronauts on spaceship Earth, and we have a collective duty to maintain its systems, protect its life support, and ensure it remains a vibrant and livable world for all future generations. The silent, ancient clusters like NGC 3201 have no stake in our survival, but their silent, enduring presence reminds us that we are the only ones who do. They are a mirror reflecting back not just our curiosity, but our responsibility. Yet for all our sophisticated tools and brilliant theories, we must confront a humbling possibility that some secrets of this ancient cluster might forever remain locked away just beyond the grasp of our understanding. The very nature of its journey stretches across billions of years, a timescale so vast it defies human comprehension. We are essentially trying to reconstruct a single day in the life of a centenarian based on a blurry, faded photograph from their childhood. The specific, singular event that sent NGC 3201 on its backward path, be it a precise gravitational slingshot or a specific galactic merger, may be lost to the void of deep time, its details eroded by the relentless entropy of the cosmos. We can identify the class of possible causes, but we may never pinpoint the exact culprit with absolute certainty. This inherent uncertainty isn't a failure of science, it is its very essence. The pursuit of knowledge is not a straight line leading to a final, complete answer, but an endless, expanding frontier. Each discovery peels back a layer of the cosmic onion, only to reveal more complex and fascinating questions beneath. The unknown is the engine of scientific progress. It is what keeps researchers hunched over computer screens late into the night and inspires them to design ever more powerful telescopes. The mystery of this cluster's motion is a perfect example of a question that is far more valuable unanswered, for it continues to drive innovation, collaboration, and a deeper, more nuanced appreciation for the complexities of our universe. Perhaps the greatest unknown is whether we are even asking the right questions. Our entire framework for understanding this phenomenon is built upon the foundation of Einstein's general relativity and the standard model of cosmology, which includes dark matter and dark energy. But what if our foundational models are incomplete? What if the anomalous motion of this cluster is not a puzzle to be solved within our current understanding, but the first faint hint of a deeper physics we have not yet even conceived? Its path could be a subtle clue that on galactic scales, gravity behaves in ways not perfectly described by our existing equations, pointing toward a new theory that seamlessly blends the quantum world with the cosmic. This possibility is both daunting and exhilarating, suggesting that the ultimate answer might not be found in a finer measurement of the cluster, but in a revolutionary new chapter of physics itself. Some mysteries may remain simply because the universe is under no obligation to make itself fully comprehensible to us. We are a young species on a small planet, using our limited senses and intellect to try and decode the workings of a reality that is billions of years old and unimaginably vast. There is a profound beauty in this acknowledgement of our limits. It cultivates a necessary humility, a virtue that is as crucial to the scientific mind as relentless curiosity. It reminds us that wonder is not a temporary state to be replaced by knowledge, but a permanent and essential companion on our journey of discovery. The true legacy of NGC 3201 may not be the solution it provides, but the boundless curiosity and humble awe it continues to inspire in all who dare to look up and wonder. Behind every data point and every published paper, there are scientists whose lives become intertwined with the mysteries they seek to solve. To truly understand the pursuit of NGC 3201, we must step into their world, not just of equations and simulations, but of late nights, sudden breakthroughs, and the quiet weight of the unknown. When you sit down with the astronomers who first spotted the cluster's anomalous motion, you don't just hear about velocity curves and statistical significance. You hear the palpable excitement in their voices, the kind that comes from staring at a screen and realizing you're seeing something that no one in human history has ever seen before. One researcher described it as a visceral thrill, a moment where the abstract numbers on her monitor suddenly transformed into a profound story written in the motion of stars, a story that contradicted the textbook narrative she had helped to write. That initial jolt of discovery is the fuel that powers years of meticulous, often tedious work. Yet for every moment of exhilaration, there are countless hours of frustration. Another scientist shared the agony of a promising lead that evaporated after months of analysis, a flaw discovered in a data processing algorithm that meant recalculating everything from scratch. He spoke of the emotional roller coaster of submitting a paper to a prestigious journal, only to have it returned months later with pages of critiques from anonymous peers, each comment requiring a week of additional work and defensive justification. This process, known as peer review, is the essential quality control of science, but it is also a gauntlet of doubt that can shake a researcher's confidence. They must learn to separate their personal attachment to a beautiful theory from the cold, hard demand of the data, a constant balancing act between passionate conviction and rigorous self-skepticism. The cluster's retrograde orbit wasn't accepted as fact after its first observation. It had to survive this relentless process of challenge and verification, a journey that required not just intellectual brilliance but immense emotional resilience. What becomes clear from these conversations is that scientific progress is rarely a straight line from question to answer. It is a winding path paved with collaboration and camaraderie. A young postdoctoral researcher recounted the story of being stuck on a particular gravitational model for weeks, until a casual conversation over coffee with a colleague from a different department, a specialist in computational fluid dynamics, provided a fresh analogy that cracked the problem wide open. This is the human ecosystem of science in action. The shared whiteboards covered in half-erased equations, the conference room debates that stretch long into the evening, the supportive emails sent across time zones to a struggling collaborator. The weight of a puzzle as deep as this one is too heavy for any single mind to bear alone. It is shouldered by a community, a network of individuals who celebrate each other's small victories and provide a critical safety net during the inevitable periods of doubt and stagnation. Their personal reflections reveal that the greatest instrument in any investigation is not the telescope or the supercomputer, but the collective and persistent curiosity of the human spirit, forever driven to find meaning in the silent patterns of the cosmos. This spirit of global collaboration is the silent engine behind so many of our modern astronomical marvels, and perhaps no single project embodies this better than the Gaia mission itself. While it flies under the flag of the European Space Agency, its story is one of truly worldwide partnership. The spacecraft was built with components and expertise from across Europe, but its scientific brain is a collective of hundreds of researchers from dozens of countries, including the United States, Australia, and nations across Asia and South America. This international consortium doesn't just analyze the data after it's collected. They were involved from the very beginning, designing the mission's scientific goals, developing the complex algorithms needed to process the raw starlight into precise measurements, and creating the rigorous validation checks to ensure its accuracy. The mission's operations center in Darmstadt, Germany, is a constant hub of coordinated activity, but the data it beams down is immediately distributed to reduction centers in Toulouse, Barcelona, Cambridge, and beyond, where teams work around the clock in a carefully orchestrated relay race of information processing. This model of open data sharing is what truly sets modern astronomy apart and accelerates discovery at an unprecedented pace. After a short proprietary period for the core teams to perform their initial calibration and validation, Gaia's entire colossal dataset is released to the entire world for free. An astronomer at a small university in Chile, a graduate student in India, or an amateur enthusiast in Canada has the exact same access to this priceless treasure trove as a professor at the most prestigious Ivy League institution. This radical openness democratizes discovery. It means that the person with the best idea, not just the biggest telescope or the largest grant, can make the next breakthrough. It was this very principle that allowed for the discovery of NGC 3201's retrograde motion to be independently verified and studied by teams who had never met each other, building a consensus that was robust and undeniable because it was built on a foundation of shared evidence. The challenges that make this cooperation necessary are as practical as they are profound. Building and launching a space observatory like Gaia costs billions of dollars and euros, a sum too great for any single nation to bear comfortably. By pooling resources and expertise, agencies can achieve goals that would otherwise be impossible, but the benefits run far deeper than just shared costs. This collaborative framework fosters a rich cross-pollination of ideas and techniques. A novel statistical method developed by a team in Japan to filter noise from the data can be adopted overnight by a researcher in Brazil studying a completely different stellar phenomenon. A challenge encountered by engineers in Italy during the spacecraft's construction might find its solution in a technical paper written a decade earlier by a team in California. This global brain trust, constantly communicating through shared journals, virtual conferences, and collaborative software platforms, ensures that progress is never halted by a single point of failure. When we look at the mystery of NGC 3201 through this lens, its story becomes a powerful testament to what this global teamwork achieves. The initial astrometric data came from a European satellite. The crucial spectroscopic follow-up observations to measure its radial velocity were made using large ground-based telescopes in Chile, operated by an international consortium including European, North American, and Chilean partners. The theoretical models simulating its possible history were run on supercomputers in the United States and Germany, and the analysis of its chemical composition to test the galactic cannibalism theory relied on techniques refined by astronomers in Australia and Japan. No single country, university, or individual can claim to have solved this puzzle alone. The answer, when it is finally found, will be a mosaic, with each tile placed by a different hand from a different corner of the globe, all contributing to a picture of understanding that is far greater than the sum of its parts. This is how we collectively turn the key in the lock of the universe's deepest secrets. Ultimately, this cosmic detective story, this quest to understand a single cluster's defiant path, points us toward something far greater than the sum of its data points. It reconnects us with a feeling that is both primal and profoundly human, a sense of sheer, unadulterated awe. This isn't just about solving a puzzle. It's about standing before the vast, mysterious canvas of the universe and feeling a deep, resonant wonder at its beauty and its staggering complexity. That emotional response, that catch in your breath when you truly contemplate the scale of what we're discussing, is not a side effect of science, it is its very lifeblood. It is the fundamental fuel that has powered our quest for understanding since the first humans looked up at the star-strewn sky and dared to ask why. This feeling of awe is far more than a passive emotion. It is an active, catalytic force in the process of discovery. Think about the great pioneers of astronomy. It wasn't cold, clinical calculation that drove Galileo to point his telescope at Jupiter. It was a burning, awe-inspired curiosity to see what was truly there. It wasn't just mathematical rigor that led Einstein to his theories of relativity. It was a profound sense of wonder about the nature of light, space, and time itself. Awe shatters our complacency. It disrupts our everyday thinking and opens our minds to possibilities we never would have considered within the confines of our ordinary concerns. When we encounter something that truly astonishes us, like a million stars moving in concert against the galactic flow, our brain is jolted into a different state. We become more receptive, more observant, and more creative. We are driven not just to know, but to understand, to connect, and to find our place within the grand narrative. In a practical sense, this emotional connection is what transforms a dry academic exercise into a passionate, human endeavor. A scientist may spend years on a single problem, facing down countless dead ends, failed simulations, and rejected papers. What keeps them going through those long, frustrating nights is not just discipline or the promise of a publication, but that initial spark of wonder, the memory of that first moment when they saw the data and thought, "That's impossible." And that is incredible. It is a powerful antidote to burnout, a reminder of the profound mystery that drew them to their field in the first place. This wonder is also our greatest tool for communication. We can throw facts and figures at an audience all day, but it is the shared experience of awe that truly bridges the gap between the expert and the enthusiast, between the scientist and the public. It creates a common language of amazement that everyone can speak. Furthermore, embracing this wonder is an act of profound humility. It is an acknowledgement that the universe is under no obligation to conform to our expectations or to be easily understood by our finite minds. The mystery of NGC 3201 is a gift precisely because it does not yet have an answer. It holds a door open, inviting us to step through and explore further. It keeps our quest for knowledge alive and dynamic, ensuring that science remains a living, breathing process of exploration rather than a static collection of settled facts. In the silent, backward dance of those ancient stars, we find a perfect mirror for our own human spirit, endlessly curious, resilient in the face of the unknown, and forever driven to find meaning and beauty in the cosmos. This shared sense of awe is what truly connects the scientific pursuit to the deepest parts of our humanity, reminding us that to wonder is, in itself, a way of knowing. From the gravitational tug of dark matter to the echoes of ancient galactic collisions, the journey of NGC 3201 has taken us through some of the most profound ideas in modern astrophysics. This single cluster, a tiny speck in our vast galaxy, has challenged our foundational models and forced us to think bigger, to dig deeper, and to question what we thought we knew about the cosmos. Its backward path is more than just an orbital anomaly. It is a key that has unlocked discussions about the invisible architecture of the universe, the violent history of our own Milky Way, and even the very nature of time and reality. We've sifted through the data from powerful telescopes, explored complex computer simulations, and weighed the possibilities from the well-established to the wildly speculative. And through it all, one thing has become beautifully clear. This mystery is a testament to the fact that our universe is still brimming with wonders waiting to be uncovered. The story of this cluster reminds us that science is not a static collection of facts, but a dynamic and ever-evolving conversation. Every answer we find, every theory we confirm, simply peels back a layer to reveal a new set of questions, a fresh horizon of mystery. The pursuit of knowledge is a journey with no final destination, and that is what makes it so exhilarating. Whether the ultimate explanation for this retrograde orbit turns out to be a past encounter with a dwarf galaxy, the subtle influence of a dark matter clump, or something we haven't even dreamed of yet, the process of seeking the answer will have already expanded our understanding in countless unexpected ways. This endless cycle of question and discovery is the very engine of human progress, driving us to build better telescopes, develop new theories, and continually refine our picture of reality. So as we bring this exploration to a close, we invite you to carry this sense of wonder with you. The next time you look up at the night sky, remember that it is not a static painting but a dynamic, evolving, and deeply mysterious place. The silent, ancient light from clusters like NGC 3201 is carrying stories across millennia, stories of cosmic violence, of invisible forces, and of a universe that is far stranger and more magnificent than we can often comprehend. Let that feeling of awe fuel your own curiosity, whatever form it may take. We would love to hear which theory you find most compelling or what questions this journey has sparked for you. Share your thoughts in the comments below and join the conversation. If you enjoyed this deep dive into the universe's secrets, make sure to subscribe and hit the notification bell so you don't miss our next adventure into the unknown. Thank you for watching and